Okay, so far we've studied the steel rule. It's a handy device, but it's not good for every measurement. For example, there's a lot of interior measurements that you can't get the gauge into. So what are you going to do? When a gauge isn't the right gauge for the job, it doesn't necessarily mean that you go to the next expensive gauge. What you need to do is find a gauge that solves the problem that the gauge that you're using is having. One way to solve that problem is using the combination set. Combination set has 3 different devices on it. It has the square head, the protractor head, and the center head. Later on we'll show you how we use each of these heads to resolve some of the issues that the scale has by itself. It helps you line up your characteristics with the scale itself. But sometimes even this isn't good enough. So another thing we're going to look at is the calipers. We have calipers that are designed to measure the inside of a part. We have calipers that are designed to measure the outside of a part. We have calipers that are designed to actually make a circle. The problem with these calipers is they don't have any measurement on them. So what can we do to resolve that problem? Well, we have to transfer it from the part to the scale where we have the measurement. The scale becomes the standard. We have the measurement that we have to read from the scale, which has a standard. But if we had a caliper that had the standard built into it, what could we do with that? That is when you get the slide caliper. And it has a variety of functions built into it for measuring ID, OD, step, and much more.
Calipers and vernier instruments. When using a rule, there's often ways that you can generate errors. The top illustration, you can see that you can generate an error if you end up bending the rule. The rule needs to be straight in order to get an accurate measurement. Also, if you cock it, instead of having it along the direction of the measurement, you're going to have an error in your measurement. The correct way is to have a light force, holding the rule against a suitable surface, for alignment with the line of measurement. Or you can have a properly sized auxiliary support to hold the rule to the line of measurement. You'll also have error. If you have an obstruction that causes instability, that will require a different method. One of the difficulties of using a rule, especially a longer rule, or making measurements that are over a longer length, is that it's hard for your eyes to keep track of both the reference point and the measure point at the same time. So, as you look at the reference point, to make sure it's lined up, and then move to the measured point to see if it's lined up, the reference point may actually move. That can create error also. That's called manipulative bias. What features can we add to the rule to resolve the problems we see when we try to use them? One feature we can add is an accurate surface to align the reference point. Here we've developed a depth gauge, that is a steel rule that goes down into a hole, but it is supported along the reference surface, by a foot, or we call it a head. The head is precision ground, so it is flat, and perpendicular to the rule that assures a line of measurement that is accurate. We can also put a hook on the bottom side, so that we know that we have actually reached the bottom of the hole. If it's a through hole, it may be difficult to see from the top of the hole, but the hook will give you a positive stop. There's a variety of other attachments we can use, and they come in the combination set. The combination set has a center head, a protractor head, and a square head. They are attached to the steel rule referred to as the blade. It also comes with a scriber built in. The combination square resolves the problem where you're trying to eyeball a rule where there may be a radius or other obstruction. You can use a reference block as shown on the right, but it has poor reliability and very difficult to control. The combination square is attached to the rule, or the blade, and that provides satisfactory reliability and much more accurate measurement. You can also identify issues such as height by adding another accessory to the rule in addition to the square head. And you can also check squareness along the length of the rule using the square head. You can also use it for depth measurement. Notice in this illustration that B and D show error by using the device incorrectly. You must make sure that the rule is correctly in line with the measurement. The protractor head uses the protractor head is a reference point, and it uses the blade or the rule as the measure point. It is used to measure angles. The angle measurement is built into the head itself. Sometimes it's difficult to get a diameter because it's hard to assure that you have the full diameter and not a chord. However, using the center attachment, it will assure you that you are lined up to the center. In fact, if you were to scribe across a circular feature with the center feature, you may find out that the part is out of round because the diameters will not cross at the center. Another important point is to make sure that the scale that you choose to use is on the side of the head. You don't want to attempt to read across the blade to the scale on the opposite side. That requires sighting, which is not reliable. Reliable measurement with combination sets. Observe all applicable precautions for steel rules. Ensure that the heads have not worn excessively. Be sure that the line of measurement is parallel to the blade. Apply holding force to ensure stability during the measurement. Be sure the scale is read in the proper direction. Work from a plate. Be sure the blade is in contact with the plate. Take particular care to minimize parallax error. Check all attachments for wear and squareness. If attachments are used, keep overhang as short as possible. One way to improve your measurement is to have contact with your reference point and your measured point. One way to have contact with those points is to use a simple caliper instrument. Here you see examples of these instruments. You have the divider, the outside caliper, the inside caliper and the hermaphrodite caliper, which has one side for outside and one side for inside. Let's say you wanted to make a circle of a particular diameter. It's possible to do it with a steel rule by trying to keep the reference point at one location and rotating that rule around that location to generate the circle. However, it can be very difficult again to control both the reference point and the measured point at the same time. Another approach is to have a radius bar, where you have 2 points machined onto a bar, and rotate that bar at a precise diameter. If you want an adjustment, however, you can use the points on an adjustable caliper, which will allow you to make a variety of different circles. Circles are made with the dividers. You also have the outside calipers for measuring ODs, inside calipers for IDs, and the hermaphrodite caliper for line-to-end measurement from a center point to an OD. The problem with the calipers is they don't have any scale on them, so that means you have to use them, and a scale, to determine the actual size that you're measuring. So, what if you were to combine those features of contact points and a scale? What you end up with is the pocket slide caliper rule. There, you're using the rule as a part of the device and moving features on that rule. So, you can do direct measurements to the scale of ODs and IDs. Here you can see how the jaws are used for measuring ODs and for IDs. Now, one approach of measuring a feature would be to use the hook rule. But what's nice about the slide caliper is you have contact to both the reference point and the measured point. It's still important, however, that when you're using a caliper that the scale is in line with the measurement. If it's out of alignment, you will have error. Advantages of the slide caliper. It combines the rule inside and outside calipers into one instrument. It provides positive contact with the reference and the measured points. It substitutes line to line for line to edge readings. It has built-in memory. The disadvantages is there's no wear adjustment. If it wears too much you have to throw it away. It's subject to misalignment. You have to make sure visually that the scale is in line with the measurement. There's limited discrimination and you cannot caliper inside to outside part features with the slide caliper. Reliability checklist for scaled instruments. Before using a scaled instrument, you should inspect it for wear and tear. Set up a periodic system for inspection depending on the use. Inspect contact surfaces with a magnifier for wear or abuse. Remove burrs from sliding contact surfaces. Compare readings against an instrument of higher precision, greater accuracy, and with known calibration. Check all mechanical actions for proper functioning. Clean and lubricate internal parts. Pass check alignment against square of known calibration in use. Never use a measuring instrument for a hand tool, such as a scraper or a chip, or a burring tool, a mallet or a sledgehammer. Never use beyond the intended size range. Don't force it open. Never use beyond discrimination or recommended precision. Keep contact force to a minimum. Avoid excessive movements causing wear. Clean both part and instrument before using. Substitute mechanical support for hand support whenever possible. Guard against parallax when reading. Have entire setup rigidly supported. Do not over-tighten anything. Care of the scaled instrument. Lubricate instruments before replacing in the case. Keep away from moisture. Do not pile instruments together with other objects, such as in a toolbox. Do not mark tools in any way that interferes with the use, and do not hesitate to throw away Warner defective tool. There's a way that you can actually increase your resolution without changing the tool very much. It's to add amplification to a ruled instrument using the vernier scale. It allows you to gain more resolution while remaining readable. That is, you shouldn't have to use a magnifying glass if you want to get more resolution. To read a vernier in inches. Step 1. Select the nearest whole inch. Step 2. Add the next whole 100,000ths of an inch. Step 3. Add the next whole 25,000ths of an inch, and finally add the nearest 1,000ths of an inch. When using a vernier scale, you may have to read left to right or right to left, so make sure you pay close attention to what direction the vernier is going on your device. Here's an example of a vernier scale on a hand caliper. Advantages and disadvantages of vernier scales. The advantages are: amplification is achieved by design, is not dependent on moving parts that may wear or go out of calibration. There's no interpolation possible in reading, let alone required. There's no theoretical limit to the scale range. That is, you can have a vernier scale used on any length. Zero setting adjustment is easy. The disadvantages. The principal disadvantage lies in the instruments on which the verniers are used. The reliability of reading depends more on the observer than most instruments. The discrimination is limited and there is no way to adjust for any errors other than zero setting. Now, when you look at a measuring device, you can divide it into two different types of features: functional features and metrological features. On the vernier caliper, the functional features are scale being viewed, clamping screws, the beam divider, setting holes if available, nibs for inside measurement, fixed jaws for outside measurement, the movable jaw versus the fixed jaw, adjusting screws, the vernier scale plate, the vernier scale, the adjusting nut, and the nut carrier. The metrological features include the axis of the instrument, which must be always aligned to the measurement you're trying to make. You have the reference point, which is the fixed jaw, and the measured point, which is the movable jaw. The length standard is built into the instrument. It's the scale that's in the instrument. There are two measurement methods. All measurement requires these three elements: a part, a measuring device, and a standard. In the interchange method, both ends are observed at the same time. In the displacement method, ends are observed separately. Abbe's law is very important for accurate measurement. Maximum accuracy may be obtained only when the standard is in line with the axis of the part being measured. The use of a vernier caliper. Using a displacement measurement. Step 1. Observe one end, that would be to set your zero. Step 2. Observe the second end of the part simultaneously with observation of the standard. As you can see, there's the part, the displacement, and the standard built into the caliper, which is the scale. There's possible positional error if the part is not in line with the axis of the standard. Then you can have error. Steps for using the vernier caliper. Determine that this is the best instrument you have available for the particular measurement. Do not use it simply because it's handy. This is a common error. People like to use them because it's handy, but often it doesn't have the resolution. You need to be the correct gauge for the job. Thoroughly clean both the part and the caliper. Make it a habit to automatically check all contact surfaces of the part and the instrument for burrs or other obstructions. Loosen the clamping screws on both the movable jaw and the nut carrier. Set the movable jaw slightly larger than the feature to be measured. Clamp the nut carrier to the beam. Snug up, but do not lock the clamping screw on the movable jaw. Place the fixed jaw in contact with the reference point of the part feature. Align the beam of the caliper to be as nearly parallel to the line of measurement as possible in both planes. Turn the adjusting nut so that the movable jaw just touches the part. Tighten the clamp screw on the movable jaw without disturbing the feel between the caliper and the part. Read in place without disturbing the part of the caliper if possible. If not, you can remove the caliper and read it. Record the reading on scratch paper. Chalk on the part or the part drawing, but don't trust your memory. To remember the value. Repeat the measurement steps a sufficient number of times to rule out any obvious incorrect readings, and average the others for the desired measurement. Loosen both clamps. Slide the movable jaw open and remove the work if not already done. Clean, lubricate and replace the instrument in its box. Ask yourself what errors may remain in your measurement geometry of the vernier caliper. You have the plane of the caliper, the line of measurement, the reference point, the measured point, and the measured distance. The line of measurement is the shortest distance separating the reference point and the measured point. If the part is rectangular, this is the perfect line perpendicular to the reference edges. Therefore, the line of measurement must lie in the plane of the caliper. The line of measurement must be parallel to the beam of the caliper, and all deviations from the above will be included as error in the caliper reading. The top illustration shows that accurate measurement. You can rotate the part and that will still be accurate. However, the middle picture shows it being cocked in relationship to the line of measurement that will be inaccurate. It will actually measure a longer measurement than accurate. It can also be cocked from side to side. That's also inaccurate. The met line of measurement is not in the plane of the caliper. When trying to measure a circular feature with a caliper, pivot it from the fixed jaw, slowly closing the movable jaw until you can just feel it at the center. That is the most accurate way to determine a diameter. One of the things you absolutely want to avoid is using too much force on a caliper. Although exaggerated in the picture, you can actually flex the caliper, creating error. Do not over-tighten and create a significant gauge force. The force could either flex the caliper or it could actually change the part. Either way, you're going to end up with error. Here you can see other errors. The correct size is when it's properly aligned. Undersized or oversized can occur when it's cocked. Also, look for wear. You'll get incorrect measurements if you have worn jaws. The jaws must be parallel. Otherwise you will get undersized and oversized measurements. Repeatability, accuracy, and precision. Repeatability is one of the measure of repeatability of one measurement on one part with the same instrument. An observer does not measure the accuracy of the instrument, does not measure the precision of the measure. Does not measure the precision of the instrument, does measure the combined precision of the observer and the instrument for one portion of the entire range, and can measure the accuracy for the combined observer and instrument for one portion of the entire range, if the true value of the test part is known. The shape of the part would allow a high repeatability, but the measurements may all be correct or incorrect. Notice you have a small feature that can cause that jaw to cock because of the pressure is concentrated in one area. The vernier depth gauge. Vernier depth gauges increase the accuracy that you can get. Although adding a vernier scale to a depth gauge increases the resolution that you have versus a direct reading depth gauge, you can still have errors if it's improperly used. The reference line from the vernier head must be lined up with the measured line. If the part feature is unsuitable for a reference point, you cannot use it. You have to make sure that the base is not lifted off the reference line by having too much force under the depth rule. You have also to make sure that it is not cocked, or you'll have error in your depth measurement. Steps for using depth gauge with vernier height gauge. Thoroughly clean and inspect the attachment. Fasten it to the movable jaw. Set the depth gauge rod with its end in contact with the surface plate. Write down the reading. Do not rely on memory. Raise the movable jaw to clear the obstruction on the part. Place the height gauge in position and lower the movable jaw until the rod of the depth gauge contacts the measure point of the part feature. Note the reading. The difference between this reading and the reading in step 4 is the height of the measured point above the reference surface. There's a variety of surface gauges. A way to expand the functionality of a rule gauge is to use a reference point, or reference plane, using a surface plate. The gauge has more reach, but the flexibility is limited by the location of the granite block. That is to say, you can't always take a granite block with you, as easily as you can take a hand caliper. Here's a vernier instrument that is used on a granite block and it's the height gauge. Here you have to have the granite block that works as the reference plane. And then the movable features of the vernier height gate is the measured point. You have the functional features of the vernier height gauge, the column, the main scale clamping screws. Nut carrier. Fine adjustment nut. Fine adjustment screw. Vernier plate. Scriber. Clamping screw. Slide. Arm accessory clamp. And the base. The metrological features are the axis of the instrument, the length of the standard, the line of measurement, the observed value, the two measured points that are optional, and the distance under observation, and the reference plane. You also have to be careful when using height gauges. When measuring long heights, they can wobble and create error. You can push too hard on the height gauge tips, causing it to cock. Especially if you're not paying attention. The line of measurement is not parallel to the column, or the measured plane is not parallel to the reference plane. You're going to have magnification of instrument errors. The base should be wider than the height for the most accurate measurement. And it's also true for trying to measure parts. If you have a surface plate, the most reliable measurement is when you have the longest dimension of the part on the plate. Suggestions for reliable height gauge measurement. Do not use height gauge for measurements requiring greater discrimination. Know that the instrument is in calibration. Observe scrupulous cleanliness. Move the height gauge by the base, not the column. Allow the height gauge, surface plate and part to stabilize, that is, reach the same temperature. Prefer low setups to high ones. Repeat each measurement. Question the alignment of the instrument reference surface and part for each use. Know that the surface plate is sufficiently flat for the desired measurement. Let's watch the vintage movie once again for tips on using the ruled instruments with accessories.
One modification of the steel rule is in the form of a depth gauge useful for measuring slots and holes. Be sure the depth rule is held at right angles to the face of the work. Lock the clamping screw. The narrow rule will enter holes down to 3/16 of an inch in diameter. The rule depth gauge is convenient to use in measuring the depth of keyways. Another application of the steel rule is in the combination square. Among its many other functions, the combination square is used in laying out work. If the material is of steel, a solution may be used to make layout lines more easily visible. Using a rag that is free of oil or grease, swab the work sparingly with the solution. A drawing shows a plate in which two holes are to be drilled. One hole is to be 3½ inches from one edge and 3½ inches from the other edge. The second hole is to be 4 inches from the first hole and 4½ inches from the edge. The rule is set for the center lines for the first hole, 3½ inches from the edge as specified by the drawing. A scriber is selected. Holding the head of the combination square against the work, scribe the line along the end of the rule. The groove in the rule should be on top, otherwise the scriber may make a nick in the line. The center line for the first hole is to be 3½ inches from this edge. The combination square need not be adjusted for this dimension, being already set on the 3½ inch index. According to the drawing, the second hole should be 4 inches from the first. Set the rule 4 inches more to the 7½ inch index. According to the blueprint, the center of the second hole is to be 4½ inches from this edge. Set the rule to the 4½ inch graduation on the scale. The juncture of the lines is nicked with a center punch. Use a magnifying glass. It assures accurate centering of the punch. A light tap is all that's required. A heavy blow may shift the punch. Modifications and the measuring instruments with which they are employed find wide use in the machine shop and layout department. The usefulness of any tool, even though it's only a simple instrument like a steel rule, is maintained by good care. Well-oiled tools kept in good order mark the competent craftsman.
Now let's watch a video that helps us use the vernier scale on measurement instruments.
Hi, I'm Bob Welds, and this is how to read a metric vernier caliper. There are different kinds of vernier scales designed to do different jobs, but they all work pretty much the same way. Today, we're going to look at a metric vernier designed to measure to the nearest 1/50th of a millimeter. That is 0.02 millimeters. See how 1 divided by 50 equals 0.02? Now, the first thing we're going to measure with our vernier caliper is nothing. That's right, we'll measure 0. It may sound like a silly thing to do, but we're going to do it for a couple of reasons. Let's do it and you'll see what I mean. You see, when the calipers are fully closed, measuring 0 width, you can see the places where you can take measurements. These surfaces are where the two parts of the calipers line up. You'll also notice that there are gaps in a couple of places on the calipers. These are not places to take measurements, so don't mess up by putting something in one of those gaps. Now, with the calipers closed, you can see where you're supposed to read the main scale. There are two scales on a vernier caliper, the main scale and the vernier scale. I'm going to erase the vernier scale and let you just look at the main scale first. You see, the 0 mark points to the place where you're supposed to read the main scale. Right now, it points to 0. Do you see that? Good. Let's read the main scale first. It's super easy. I'll close the calipers on this workpiece and we'll see what the main scale says. These marks represent whole millimeters. So the reading is 1, 2, 3, 4, 5 millimeters. Just be sure to look at the 0 mark and not at this part. That's a common mistake and it'll give you the wrong reading. So the reading is 5 millimeters. That's pretty easy, right? Before we move on to the vernier scale, let me show you what it's going to tell us, okay? Let's say when we looked at the main scale, the reading wasn't right on the mark like it was last time. Let's say it looked like this. See how the mark is between 5 and 6 millimeters? It looks like it's a little beyond halfway. You see, the vernier scale is going to tell us almost exactly how far over the mark is. Okay, you're ready to see the vernier scale, but I'm only going to draw the main part of it first. Now, you see the marks number from 0 to 10. Each of these marks represents a tenth of a millimeter. They're going to tell us the tenths of a millimeter, and here's how they work. Look carefully, and you will notice that one of the marks on the vernier scale lines up better with the main scale marks than the others. Which one looks like it lines up best to you? I'll zoom in and let you look. Let me show you a hint about where to look on the vernier scale to see where the marks line up. You see how our pointer was a little more than halfway between marks? That means the vernier scale will line up a little past halfway. Now, do you see the mark that lines up better than the rest? It looks like the 7 is lining up. The 7 means 0.7 millimeters. But this caliper can measure even more accurately than that. I'll redraw all the marks and let you look again. Now, see that the mark next to the 7 lines up best. But what is the value of that mark? Remember how this caliper had a label that said 0.02 on it? That is what each mark is, 0.02 millimeters. Let's count up on the vernier scale to be sure we've got it. This 6 would be 0.60, the next mark 0.62, then 0.64, 0.66, 0.68, 0.70, then 0.72. The reading is 5.72 millimeters. Pretty neat, huh? I'm going to let you try a few. We're going to start off easy. I'm going to draw a caliper that only reads to the nearest tenth of a millimeter. just to be sure you're with me. I'm going to show you the overall picture first, then zoom in to let you see the vernier better. Okay? When you see Sparky's pause the video and write down what you think the reading is. The reading is 16.2 millimeters. Let me step you through it just in case you missed something. Here are the whole millimeters from the main scale. 10, 11, 12, 13, 14, 15, 16. Okay. And you see how the reading is just past the 16 mark? So we'll look to the front of the vernier scale for where the marks line up. And there it is, at the 0.2 mark. So the reading is 16.2 millimeters. Got it? Okay, let's go for broke and see if we can read the full 0.02 millimeter resolution. Ready for this one? Again, I'll show the whole caliper, then zoom in to let you see the vernier better. Here we go. Pause the video and write down your answer. Now, I know this is hard, so before I give the answer, I'm going to point to the place where the vernier lines up. Does that help? Take a minute and check your answer and be sure it's correct. The reading is 19.16 millimeters. Okay, let's try another one. This time I won't give any hints, but I will zoom way in so you can see the calipers really well. If you get this one, you pretty much know what's going on. Pause the video and make sure you can read the whole millimeters. Did you say 12 millimeters? Okay, let's do the hard part and read the vernier scale. I'll zoom in and let you take a closer look. But first, remember the trick? See how the reading is beyond halfway between the marks? That means we need to look on the high side of the vernier scale. I'll slide the view down there and let you look. Now here we go. Pause the video and look carefully. The mark that lines up best is here. Now, what number is that? This is the 0.7 mark. So 0.72, 4, 6. The answer is 12.76. That's about all the time we have for now. Vernier calipers are hard to read, but with a little practice, I'm sure you'll be able to do it without too much trouble. I'm Bob Welds, and these are Weld Notes.